Well, great. Thanks everyone for being here. My name's Heather Lammers. I'm a Ph.D. candidate in the mining engineering department. I've been asked to give a brief introduction about me and my professional teaching and service experience, and then we'll jump into mine closure. Where do we start? So a little bit of background about me. I did my BS in geological engineering at the University of North Dakota. I did my MS at mining engineering from here at Mines. And as I mentioned before, I'm currently a PhD candidate in the mining engineering department. I've most recently served as a senior engineer and senior technical principal for WSP Golder for about 15 years. In that role, I was a lead strategist for mine closure and reclamation, and also mine waste and water management. I was a technical lead for several mine waste facility lifecycle design projects and also oversaw construction of them. As with most consultants in a senior role, I was also responsible for team development and management, and also client and project management. Many of you know that I'm a pretty big fan of the University of North Dakota hockey team. Played there as an undergrad. I'm also a really big baseball fan, go Cubs. And family is my world. Me and both of my dogs, Copper and Kyanite. So I want to give you a little bit about my professional kind of experience. I like to say it generally follows most components of the mine life cycle. So from performing oriented core logging early in my career, I did a lot of that to identify subsurface structure and site conditions for future facility development. I performed like pre-mine development assessments and baseline studies to establish the existing conditions of an area before we go in for mining. I also did that for specific facility site characterizations to assess like foundation conditions, hydrologic regimes, things like that. I've contributed and led design efforts, both site-wide and for specific facilities, including tailings storage, heap leach and waste rock facilities, open pit design, and also water management facilities. I've overseen construction specific to facility design and site-wide mine closure, and also operations for active tailings and water management at a TSF. I think perhaps though my most favorite experience has come during closure and reclamation, where I feel that kind of the mine design comes full circle. And there's several competing different design criteria that comes into play, making it a challenging space to work in. So I've been a TA in the mining engineering department, working with both Dr. Miller and Dr. Osbey for several classes, including underground mine design and mine evaluation and design, senior design at the undergraduate level. And then I've also been a TA for mining and mineral resource development, advanced underground mine design, and also advanced rock mechanics at the graduate level. I also lead the active learning design component in lab for the underground mine design course at both the undergrad and graduate levels. The span of 2019 to now has included periods of in-person, remote, and hybrid teaching. I've also been a lecturer for the Tailings Center, specifically the TSF Planning, Siting, and Design course. I've also assisted several of my WSP Golder colleagues with their course material prep for their lectures with the Tailings Center. I also assisted with the online course development in support of the professional master's program, specifically the mine waste, water, and closure component. And then, as I mentioned, as part of my senior role, as part of my role as a senior technical principal with WSP Golder, I was responsible for developing and delivering internal and external training programs on the fundamentals of Civil 3D. That was I'd say a design software course specific to the type of projects WSP Golder typically led. And then also general and topic specific courses in mine design fundamentals, tailings and mine waste management, and of course, mine closure and reclamation. So service for me has been a fundamental component and dominated a majority of my career in industry and here at Mines. In industry, I'm a member of both SME and MMSA. So at SME, I have served on both the national and the Colorado section board of directors. I'm currently the past chair of the Colorado section, and I'm also currently the intern of the National Board of Directors. I was just appointed to the Responsible Mining and Underground Construction Strategic Committee, so working to kind of implement some of the more broader plans of SME in that space. I also currently serve on the Awards Ad Hoc Committee, the Government and Public Affairs Committee, and then I'm supporting the Minerals Education Coalition right now in some K through 12 outreach. Previously, I've also been on the Young Leaders Committee. I've served on the Environmental Division Bylaw Ad Hoc Committee, and then the Robert E. Murray Innovation Scholarship Committee. For MMSA, I currently serve as a mentor to SME YLC through that. So kind of partnering more with like mid-career guidance for young engineers and scientists. At Mines, I've assisted with the Industry Advisory Council for the Mining Engineering Department, specifically in some of the Mines at 150 events. I've previously been the coordinator for the Graduate Experience Peer Mentor event. I was the academic chair for the Graduate Student Government for a couple of years. I was also part of a graduate student rep to the Faculty Senate and a member of the Tech Fee Committee. So enough about me. I kind of want to talk a little bit more about mine closure. So what does this mean? Like, we typically think of mine closure as starting, after we're done extracting the ore, after we're done processing, we've done our decommissioning and we've completed our reclamation, and then the land is returned to some end use purpose. That's in general terms what mine closure is. In a broader sense, we have three really key goals to address at mine closure. We want to maintain physical and chemical stability of any existing surface disturbance and underground disturbance areas. We want to maintain ecological and environmental stability, and then we want to make sure that we have an established post-closure land use. And that post-closure land use, deciding what that is a multi-stakeholder engagement process. And it typically starts at the very beginning of mine planning. So there's been several guidance documents developed, I'd say, over the past 20 years, with the most current influential documents, I think, highlighted here. So the first one being in 2018, that really kind of came out as a joint effort between the Asia Pacific Economic Corporation and Golder, and it was to develop a mine closure checklist for governments. There was a big push recognizing that not every mine facility has a what we call a closure and rehabilitation plan. And part of the reasoning behind that is because there just wasn't a consistent government initiative worldwide to implement consistent closure practices. So this was kind of like the first step in educating the governments for how they would go about starting to consider some of the mine closure aspects when they're starting at mine permitting. So in 2019, the International Council on Mining Metals delivered the Integrated Mine Closure of Good Practice Guide. And this was really a global effort by many of our mining company leads, our bigger mining companies, to kind of consortedly put together guidance for everyone globally on how to close a mine. In 2020, we saw a little bit more of a initiative moving forward with tailings. So the Global Industry Standard on Tailings Management was developed by the Global Tailings Review. It's specific to tailings facilities, and a couple of unique terms that it really brought to light. These aren't new terms, but they were made part of common conversation, and that's landform and safe closure. Both of these terms have different meanings. The idea with landform being to restore the land to the previous use or to a landform that isn't capable of causing any sort of destruction downstream. And then safe closure being what will be eventually, hopefully, a series of guidance that really is facility specific and then also at the site-wide level. So then in 2021, the World Bank Group and SRK, another consulting firm, developed Mine Closure, a toolbox for governments that was a little bit more of a build on the original 2018 document, giving a little bit more framework for those governments when they were making a bit of decisions. And then ICMM came out with the tailings management, a good practice guide, which again is specific to the tailings facilities, given that there's a focus on that right now. And then in 2022, continuing that kind of theory, the U.S. Society on Dams gave us the USA regulations and safe practices for closure of tailings dams. So again, kind of tightening and more firming our guidance up around TSFs. So there's always kind of a thought too that we should be integrating like corporate closure guidance in all of our practices. You know, each company has its own kind of standard of what they care to implement at closure and kind of what their goals are at each facility. A lot of that's tied to your local government guidelines and best practices within the area. A lot of it's tied to your permit requirements and perhaps what promises you made to a local community. There's been several other guidance documents over the years. The big one I can think of is the GUARD guide, another initiative led by Golder to develop the acid rock drainage guide that we still use today. So some initial considerations. So I like to think of closure as having two stages. You know, there's an active closure and then a post-closure stage. So during active closure, you can think that's when we're doing active closure work. So we're decommissioning facilities, we're doing demo, earthworks, we're putting cover in. And then your post-closure is kind of really where we're evaluating all of the work that we had done. You know, have we achieved the water quality or the discharge quantities that we thought we were going to? You know, is the cover system that we installed erosion resistant? Are our facilities stable? You know, is the biodiversity that we had hoped would come back or attract, is that stable and thriving really? You know, another consideration is concurrent reclamation. The mine picture to the right is next gen. It will be a new uranium mine in northern Saskatchewan. And because the tailings are likely to contain radioactive material, or it is uranium, they're going to be pumped immediately back underground into chambers, and they're going to be closed systematically as the volume requirements are the mass balance between the plant and the excavation of the underground chambers goes ahead. So that's kind of just one example of how we can integrate some of the closure practices during operation. You know, there's considerations for, are you surface or underground? There's going to be different closure practices for each. What commodity are you in, or what processing method are you using? Do you have sulfides? You know, are you worried about oxidation of materials? All of those things kind of need to be thought about, and we like to call that part of the start of your checklist. So with my closure, there's some typical components here that I listed. And again, this isn't an exhaustive list, but we have investigations that we perform. You know, we consider a final configuration of all of the facilities. You know, we consider whether there's a cover system that goes onto it. And then, as I mentioned, in that kind of post-closure phase, we're doing all of that performance monitoring. So when we talk like investigations, what we're really looking for are areas of concern. You know, are there areas that we need to account for at the closure stage? You know, is there a location of saturated zones? Are there slimes? Can we predict any of the settlement, whether that's by self-weight or whether that's by placement of a cover system? We need to always look at characterizing the foundation, whether we're adding liners, you know, a buttress to a facility. Are there toe constraints to it? Do we need to keep the toe, and are we looking at potentially cutting back into the slope to create a shallow, more stable and gradual slope? We do a lot to identify and characterize borrow sources that are available. You know, when we talk about cover materials, you know, the hope and the intent is to source things locally rather than procure them and bring them onto the site. And then similarly with revetment materials, you really want to kind of understand what you have readily available and attempt to kind of design your closure around that. You also want to understand the site-wide climate, the climate, and also the water conveyance. And all of those kind of investigations feed into what this final configuration is going to look like. You know, are you shedding or ponding water on your surfaces? Do you need to shallow up your slope to maintain physical stability or maintain placement of a cover system? You know, with the cover system, everything with that lies in your water balance. You know, is your aim to store and release? Is your aim to allow infiltration into your facilities? Does it need to act as a barrier? Is there something that you're needing to encapsulate below? And then part of that post-closure, that performance monitoring, we're looking at erosion of the dust, whether there's dust transport, whether there's cover material that's maybe eroding, and we're now seeing the material that was supposed to be encapsulated. Seepage from any of the facilities, we look at that. We look at any sort of stability issues we may see going along with the cover system and maintaining stability and resisting the erosion of the cover system. Vegetation growth is key to that. And then, of course, like I mentioned, biodiversity. We want to make sure that we have diversity in native species, and we also want to make sure that we in plant species, and we also want to make sure that we have native animal species there as well. So the final configuration is one I want to talk a little bit more about. So as with all things mining, the balance of water becomes critical. When we think of like a final configuration, we need to consider how we're going to route that surface water. During that active closure phase, we're likely, not closing all of the facilities at once, but we're rather sequencing each based on, say, like a return of your investment. Did you bond a facility independently, and are you trying to release some of that money back? Is the facility still a critical use facility until the end of mine life? And then, is there a potential for us to begin reclamation of any of these facilities in parallel with late stage operation? It's very unlikely you will have closure construction and at that active closure period and active decommissioning going on at the same time all across the mine site. And then during that post-closure period, we need to make sure that the routing we use during that active closure achieves our post-closure goals, or we need to decide whether we need to alter this. It could be to meet like a water treatment or a storage or a discharge requirement. So then when we look at facility slopes overall, an operational slope is typically steeper. Think of like angle of repose for like waste rock, like a 1.4 to 1 slope. However, the closure slope likely needs to be flatter to resist erosion of the slope, hold a cover on it, and also maintain physical stability. There's also a constructability component that comes into this. If we were to try to place a cover system on a 1.4 to 1 slope, it's very likely that cover system will not stand on the slope, but it's also very challenging when we think about putting heavy mining equipment working on anything really steeper than a 2 to 1 slope. 2.5 to 1 is kind of a sweet spot that we see, and where the operator feels comfortable working on the slope. It's a typically safe situation to work in. When you're talking about like manual labor, like kind of the photo that you see to the right, where you have manual labor to put in place concrete blocks, you really want to keep your laborers, your people that are your installers, working on nothing really more steeper than a 3 to 1. So in that typical closure configuration that you see at the right, we're using a series of outslope benches to convey surface water towards a drop structure. And then that's where the bench width that we have is determined by the constructability of the channel on it, and also the need for flow conveyance along it. And then our inner bench slope, that length is typically determined by the ability to resist erosion. Both of these can differ from the bench configuration that is maybe already existing out there. So the picture at the left, the little schematic, kind of shows an ideal situation where we're able to use the inner bench slope lengths that are already in place and that kind of inner bench width, but that's not always the case. Sometimes your slope length may need to be shortened in order to, put a more native grass species, or it could be lengthened, if you're planting something like a more stable structure like a tree. So the drop structure that we're showing on the right, that is articulated concrete block being brought in. So it is a series of concrete blocks in a mat, and we use tracked equipment to bring each of these mats down the slope. But each of these mats have to be wired together manually. And then the reason that this is this type of robust revetment is used is because we have high flow velocities on typically that steep 3-to-1 slope. So there's a lot of flow coming in, high flow velocity, and then coming down to a concentration point. So the idea is that we're discharging everything and we're controlling that discharge point and to an outlet at the toe. So when we think of like a structure like the drop structure, the ACB lines drop structure, that itself would be considered like a critical structure. It's one that is, in addition to being very costly, it's difficult to design for. It's also difficult to construct in place. And it's very easy to make a mistake during the design or construction or the installation part of this that could cause erosion or preferential flow paths in places that you don't want. The outslope bench channels, kind of those feeder channels that come into it, those can be typically grass or riprap line based on flow velocities and volumes. And those would be considered like a less critical structure that's fed. So I want to talk a little bit about cover system. I know when a lot of people think of mine closure, they think of, oh, the cover system's kind of everything. But I hope your big takeaway out of this is the cover system is one component in a system of components. So the goal with the cover system is that we need to restore that surface to a stable natural condition. So are we trying to achieve like a chemical stability? Are we isolating that waste or a material that's below, you know, was there a muck pond down there at some point that we need to limit water or oxygen influx? Do we need to maintain physical stability of that particular structure? You know, do we need to control that migration of the constituents, you know, whether it's dust, erosion, or through water? And then we need to provide a median often to support our post-closure land use. So the cover system can support that future vegetation growth, or, you know, are you using it to grow agriculture crops? Are you using it to have farmland, you know, things like that. So when I think of like cover types, I think there are 7 of them listed here. So I think of a situation where there's no cover, you know, I'm not going to install a cover on this facility, you know, in that consideration, you know, you're not trying to establish vegetation. You typically have a non-potentially acid generating environment. Those are kind of the considerations where you can get away with not using a cover. There's also the erosion protection cover, where it's just installed. It's like typically like a coarse or a rock material. It's typically installed just to prevent the underlying finer materials from migrating. With this erosion protection cover, you can add a growth media on top of that if you're in an environment that you want to establish vegetation. The store and release cover has kind of been a big one of use for the past decade. It's a evapotranspiration cover with vegetation being extremely critical in maintaining that ability of the cover to both store and release. You typically use like a well-graded rock or soil and then vegetation over it. And this is, you know, implemented a lot in our semi-arid climates where water may be a little bit more scarce and necessary though to establish that vegetation cover to prevent like a dust erosion or just a migration of fines. There's barrier type covers where we're controlling both the oxygen and water influx. We're typically using like a compacted clay or something that's like low permeability. And then it's overlain by a coarse rock material that kind of protects that barrier or a growth media. Another cover type we have is like an engineered layer. That again is to prevent oxygen and water. So not quite a barrier, but it's typically used to you know, alternate. Maybe there's areas where, you know, within your waste rock stockpile, you need to contain, say, a PAG type material, but then you can potentially encapsulate it with like a non-acid generating type material. When you're talking like a vegetation cover, you're typically using an organic soil layer. You need to install that to support all the vegetation. And then kind of this weird one that we still consider a lot is a water cover. And I think one of the weirdest scenarios that I think we ever looked at, had to consider the water cover, was in Arizona over a potentially acid generating facility. And just the evaporation rates alone of like maintaining a water cover in Arizona were just almost nonsensical. So when we look at like picking a mine, a closure cover system for a mine, you know, we typically use like a multi-criteria assessment approach where we're looking at taking these 7, you know, cover options and evaluating them based on their technical, environmental, social, and economic performance. And within each of those 4 kind of broader topics, we would break down into, you know, a technical, like we're looking at material compatibility, you know, is the underlying material stable enough to hold your top layer material? There's constructability issues with each of these, you know, do you have enough organics to even install a vegetation layer? Are you looking at bringing those in? You know, with environmental concerns, we think erosion and water quality predictions. With social, the big one that we talk about is post-closure land use. You know, if you're planning to use crops, you probably should have like a vegetation cover being installed there. And then, of course, the economic is a portion of our consideration. You know, how much does it cost to install these systems? So I wanted to give kind of a little bit of flavor of what mine closure by facility looks like. So this, again, is not intended to be a comprehensive list. It's more to give you an idea, facility by facility, what some of those active closure considerations are and what some of those post-closure land use considerations are. So when we think about a pit, it's a big hole in the ground when we're done. You know, some of the options are, do we backfill it? Do we take our waste rock material and our tailings, and do we place that back into it? Do we then put a cover system over it? And part of this is determining the mass balance of your site. You know, if you're going to backfill with waste rock, you likely are going to still need like a staged surface disturbance. The nice part about being able to backfill with the waste rock, though, is that eventually that surface disturbance goes away and it's a little bit easier to reclaim. You know, are you going to let a pit lake form in your pit? Are you going to leave it open and then potentially buttress those steep slopes? Are you going to maintain a perimeter security so that, you know, wildlife or people don't fall down your steep slopes? Do you know where your natural groundwater is? You know, the easiest way to form a pit lake is to have recharge come from natural groundwater. So thinking of when dewatering has ceased from mining operations. Some of the post-closure land uses, these depend again on what those active closure plans are. You know, if there's backfill, could you plant a native forest or vegetation? You know, are you going to use it as agriculture? Or can you use, depending on the pit lake geochemistry, can you use it as aquaculture? You know, for an underground mine, we really think the big one of backfill, you know, again, can we put the tailings underground? You know, is this something like I mentioned with NextGen's operation with their concurrent reclamation of taking their uranium tails and putting them immediately back underground? The nice part about this, again, is it reduces your surface disturbance. It can also be a benefit to providing strength and stability to your underground openings and preventing like land subsidence. For your waste rock facility, you know, are you looking, do you have potentially acid generating material? Do you need to encapsulate that, or do you need to just put a cover over it for your post-closure land use? You know, are you looking at reshaping your closure slope? Do you need to take this from like a 3-to-1 slope back to, you know, can you take this to a 2.5-to-1 slope? These are some of the things that we review when we look at waste rock facilities. And then of course, surface water routing. You know, we really want to shed water off of most waste facilities. It's very rare that you would allow water to infiltrate. And then again, with the waste rock facilities, you can often use those for native forest, vegetation, or agriculture. With heap leach facilities, the big thing is the rinsing. There's a rinsing step that goes into this before we can close it in a similar way to a waste rock facility. And part of that rinsing, I think of like when we're doing gold recovery, we're trying to recover any gold that's remaining in there. We're also trying to capture the cyanide and maintain our cyanide code. With heap leach facilities, it's very rare that you would want to have agriculture on them. So we typically restore those to like a native forest or vegetation. And similarly for a tailings storage facility, you know, again, we're looking at that. Do we need to encapsulate or cover? One of the big considerations here is the settlement predictions. You know, we have self-weight settlement over time. We can encourage that settlement to occur at potentially faster rates. But the idea being that the surface needs to be workable, so it can't be, you know, there cannot be like a supernatant pond still on the top of your TSF and then an attempt to put a cover system over it. And then when we think of like the plant facility, that's really where your demolition comes into play. You know, your plant and any of your supporting infrastructure, that material you try to demo and salvage, and then either the supporting maybe facilities, say you have a mine camp, you know, there's potential to restore those and give those back to the community. And then with the plant, there's typically a water treatment period in that post-closure time. Sometimes those can be quite lengthy. So that's part of that like post-closure consideration. So I wanted to highlight just a few facilities that I've worked on. So in your top left image, this is a copper gold located in the Southwest US. In 1985, there was a large pond. We called it a lake. This project was referred to as a lake infill project. So as you can see, in 2006, that pond has primarily retreated, but we now start to place waste material in these areas. And then you fast forward to 2019, and even in today, this site is still an ongoing reclamation. A lot of these slopes have been reclaimed using that outslope bench kind of drop structure or a strategy. And then the lake itself has a fill placed over it to basically encapsulate any of that underlying material or wind-blown material that may have gotten in there. On the top left, it's a similar copper and gold project in a different state, but this was one of the first facilities that we attempted to do a vertical straight down method where we were trying to gauge the erosivity of the material below, and we called this like a valley structure, valley drop structures, where it's basically ridged. And then each of the center lines are armored so that flow can just start coming off the top. And we did this to evaluate different slope lengths as well as different slope angles to see what material would fall. So this was one of the preliminary tests to learn that 12-inch riprap has a really difficult time standing up on anything steeper than a 3-to-1 slope. So that's kind of one thing that we do for researching different cover systems and different revetment materials. On the lower left is just an example of a TSF and iron tailings. Some of the considerations that we have to think about when we're thinking about closing the TSF is the amount of water that's being deposited in with the tailings and how we're going to handle that at closure to create a stable configuration that's also workable, that we can also recover on. The top right is a coal mine. This is a project where we attempted to mimic the natural topography. So it's one of the first truly landform designs that I implemented. And here we learned that the chinking, the appropriate placement of the rock, and how the angularity of it, if it's not placed correctly, can create preferential flow paths. And basically we had water flowing underneath the riprap versus on top of the riprap, and then it percolated into the coal and started eroding the coal. One of the more fun locations that I've worked in is the diamond mine in the lower right. That's in the Northwest Territories of Canada. There we have to do extensive climate studies when we think about closing. It's not only a lot of the mines up in that area use the snowpack as more of a containment, a temporary containment, and they use the frost line as a permanent containment. So when they build their structures, their intent is to maintain a frozen layer underneath most of the like adverse constituents, things like that, any of the materials that may potentially seep or leach metals. With this, it's difficult to predict because it's also difficult to predict what climate models look like. The other part that we work a lot up in these areas is more of like your rock-based cover, being that organic material is really difficult and scarce. And by the time you stockpile it, the next year it has very little organic material left in it. And then the picture here on the upper side is also in the Southwest US, again, different state than the others. But this is a facility where the tailings are still partly saturated and there are some zones of slimes. So we had to account for differential settlement in the design. So the surface itself, so on the left, you can kind of see where the ponding of water was on the top of the TSF. That's dominantly our area of concern that will have the greatest settlement over time. And then on the right, you can see that we have channels that run right through those areas. And those channels have been designed to settle differentially. So they'll maintain positive drainage towards their drop structures. And then the lower is the first that I had the privilege of working on. This one's in the Southwest US. It's a big test case that people use for performance evaluation. It's been standing in all of its drop structures, all of its channels. It's both outslope bench conveyance and top surface channels have been standing for well over 15 years now. So that one's an interesting. So mine closure, where do we start? So we've talked about reviewing a lot, like one great place to start is to review all of the available guidance documents. If you're really fortunate, there will be an existing closure and reclamation plan available. However, not every country requires that you have a closure and reclamation plan before you bond and before you receive your permits. Some older mines or those with little government oversight, they have no plan, no bond requirements. And if you are fortunate, though, these are generally updated every 3 to 5 years. So developing one of these is typically what we see when a larger company acquires assets from an acquisition of a smaller company that may or may not have had a closure plan in place. That larger company will typically start a process where they start developing these CRPs. Local government guidelines, best practices, and of course precedent within the area. I've shown you different climates, different locations. Each of them have what has been done before, at least in some sort of precedent. So that typically is the first step in your considerations and evaluations for what you want to do for closure. There's often permit requirements and social obligations. There's corporate closure guidance. So with your larger firms, the same general closure objectives are going to apply in the US as they do in Australia. It's just they don't work in isolation just because of location. They typically try to apply the same general practices. As I mentioned before, the Integrated Mine Closure Good Practice Guide and the Mine Closure Toolbox for Governments, those are 2 documents that we use as go-to documents, and then of course special topics. The next step that I would recommend is developing a facility inventory. Even at the start of your mine, say you're developing your closure and rehabilitation plan for a brand new mine, you're going to start developing that facility inventory and start understanding where facilities are located relative to each other. You're going to describe each of those facilities and what their intent are, what types of materials are going to be stored there, what type of activities are happening. You're also going to start identifying some of those potential post-closure land uses. These may become or may be social obligations. This is where that collaboration with all stakeholders becomes critical. And then, of course, you want to establish a design basis for your closure and rehabilitation. So you're going to have closure objectives and criteria. What are you trying to do and how are you going to do it? What is your water conveyance strategy? I say this a lot, water drives everything. The water balance is really critical. So with that water conveyance strategy also comes the water treatment. And this can be prevalent through your operation, your active closure and your post-closure periods. So with that, thank you very much for listening to me talk. I'll take any questions.
Thank you, Heather. This is Corby.
Hey, Corby.
How are you? First of all, I spent many hours driving young athletes across Montana and North Dakota to attend the fabulous facilities you have at University of North Dakota for summer hockey camps. So it was always a relief to arrive there. You may or may not know that I grew up in the mother of all mine closure and remediation sites in the United States, which is Butte, Montana. And so this is kind of a philosophical question. I'll give you some background. I noticed that you were talking about the engagement of stakeholders. How do you, and maybe you don't have an answer, how do you facilitate the change in attitude from stakeholders? And I'll give you an example. Back at the turn of the century, there was a facility in Butte called the Parrott Smelter. And so because of pollution, what became the Anaconda Company, they bought it and then they shut it down and they took overburden and they just buried everything. So when Butte became a Superfund site 40 years ago, the EPA came in and said, well, you know, I would just leave it. Okay. And then most recently, these stakeholders, including the governor of Montana, said, that ain't right. And so now, if you're aware of this, there is a unmine closure going on. But, you know, you see a lot of this. And in the recent consent decree that was struck there, you also see now that these slag piles by Anaconda, which were supposed to be left wild and open, are suddenly being covered. So I guess, and maybe there's no answer to this, how do you accommodate that into your future plan for mine closure or remediation? Or can you? How do you do it?
Oh man, that's challenging. I think it goes back to almost like the iterative nature of your closure plan. You know, for a new facility, it's almost easier. You know, you establish a closure and reclamation plan, you update it over time, taking all those considerations kind of into it and reframing what your closure goals and objectives are. I think for existing facilities, especially where you have competing interests, like you have the interest of the EPA, you have the interest of the government, you have the interest of the local people. It makes it challenging to, and a lot of it comes to funding, especially with the EPA. You know, they've got their list of the top priorities that they want to fund. So a lot of their maybe more aversion to some closure activities could be due to funding. But I think it becomes difficult for a local government to raise money or a community to raise money. But I think you're seeing a lot more like do the right thing. You know, if the local people want something done, there are other avenues than philanthropic outreach you can do. It's very difficult though. And getting everyone on the same page is challenging.
Oh yeah.
Yeah, but having those more higher level documents that just describe your closure objectives, having those kind of hashed out with stakeholders does allow it a little bit more leverage when you are talking to state funding or EPA kind of funding, national funding people.
Yeah, well,
but yeah, there's no easy answer.
No, it's very complicated. And I didn't mean to hit you over the head with that one, but it's an example that I pay taxes in Colorado, Montana. I'm currently funding this. So anyway, thank you very much.
Yeah.
Hi, Heather. This is Kadri Dagdalan. Great presentation. Thank you. I have one question that's related to latest practices for closing mines. That is, some corporations take the tailings and process it through the mill, and and then get the metal, the precious metal out to pay for the closing of the mine site by taking those mill tailings, second mill tailings, and dumping it into the open pit mining area and filling the pit. And what do you think about that practice?
It's actually a practice that Newmont is actively looking at right now at several of their locations. And it's part twofold, that especially for older facilities that either are in a state of inactive, they're done, there will be no more operations, they're inactive facilities, or they were in a care and maintenance or closure stage. A lot of times due to inefficiencies in past processing practices, they will run those tailings back through. It's a good practice where it works. So it's a good practice where you have your phreatic surface of your pit is lower. Your natural groundwater is lower than your pit. I think the challenge becomes if you're, one of the things I think about is if you're reprocessing your tailings, you're turning them back to soup typically, and you're going to put them into a soup, pit. It's challenging from a security standpoint of keeping people out of your pit, because once if you can't get them to dewater and settle, SK consolidate, you can't get them to do that, the surface will remain, unworkable and not really ideal for post-closure. If you're not in a situation where groundwaters are concerned, it's a great idea to put them in a pit. It allows you to backfill typically the majority of your pit and remove what's deposited on the surface. So you're removing your surface disturbance. You're freeing up the coarser material that was used to kind of encapsulate or impound your surface. So your embankment material, you're able to free that up for, say, an alternative purpose such as riprap in some of your conveyance channels. So in that case, you're not creating another source for your riprap. So there's a positive for your cash flow. You're getting money back in the gold recovery credits. You're taking the surface disturbance, which looks great socially, and it looks great for your portfolio long term. You're getting them back into the pit, so you're taking away the steep slope hazard that we have long term there, and you could potentially restore that surface, then that backfilled surface, to some sort of a agriculture. Well, probably not agriculture, but you'll restore it to some vegetative or forest, whatever the landscape is out there. So it's a practice that's being considered heavily and implemented at several facilities.
Great, thank you. Appreciate it.
Yeah. I can't see the chat. If somebody is typing a question in there, could somebody read those to me if there are any?
I'll read one that's in the chat. It's from Bo Radam. And it says, for mine closure, would you consider inventory of mine waste the most difficult aspect of closure for companies that have acquired already active mines? How widespread is the practice of very detailed inventory in location and composition of mine waste? And does that information usually get transferred if the mine well if the mine switches ownership?
Oh, great question. It is not transferred well if the mine is in historically it has not transferred well. Maintaining records at a mine, especially when it comes to the tailings, has gotten better over time, as there's been more emphasis on better understanding of the facility itself and the changes over time. But if you look at a facility that's 20 years old, it's highly unlikely that you will have a complete even depositional history of that. when it comes down to particle size, water content, things like that, it's challenging. And I do see a lot of challenges when a company acquires another company. It typically requires a lot of effort on whoever is kind of the spearhead of the mine waste to go to each facility and really truly inventory what their mine waste, not just the facility locations, but where their waste streams came from, and then gathering and interfacing with each of the facilities themselves. So asking the operators, asking the people at the mill, asking even the miners, you know, what material came from where and when. That can be a burdensome challenge. It's a necessary kind of part of the beast, especially as we look at like from an investment risk portfolio. I think there's an expectation there that if you are acquiring a company, you've done that work, or at least a good portion of it prior to that acquisition, for both your best interest and even the company that's selling to you's best interest. Did that answer all parts of that question?
I think so. I don't know if Bo's on here.
Heather, I have a question for you.
Yeah.
In our critical minerals project, we've been looking at reprocessing tailings as one potential source of critical minerals. And I was wondering if you could talk a little bit about the most important considerations for reprocessing from a closure perspective.
Reprocess from, so in a lot of ways, it'd be great if we could just reprocess all of the tailings impoundments that are sitting out. I think the challenges lie in the responsibility. As soon as you touch it, you know, it becomes your responsibility, your cleanup. So even sometimes characterizing or even doing like a simple, you know, drilling program to get any sort of information on what's currently there is challenging. I think when it comes to the interest of making money from the tailings impoundment, it kind of goes back to the last question, where like understanding just the composition of the tailings, the depositional environment, the processing methods, all of that becomes challenging for you to even be able to quantify what is within the tailings impoundment, in addition to where those critical minerals may be located. It's almost like looking at like a whole different geologic model of a TSF. From a closure perspective, it's great. I mean, the idea of being able to reprocess and put a material back in a more stable manner is great. You know, in concept. I think the challenges do lie though in the technology to actually separate the critical minerals from the tailings. I think it lies in the characterization of the impoundment to make sure that you have a good quantity and you know where it is. I think the methods to determining, like I think of if there are slimes within and locked within the impoundment itself, it becomes a hazard to excavate or work on top of or do any sort of exploration. But yeah, and I think the challenge of just, you know, whose responsibility is it once that person touches it becomes a concern.
Those are good cautionary words. I'd love to talk with you more about this at some point, because we've got lots of ideas and probably need your reality check.
Sure.
I put a chat up there, Heather, but the tailings are important. From my perspective, the first question to ask is, why are they there in the form they are? And that can be a choice or poor operation or mineralogy, and it all goes from there, right? And you know, what happened 100 years ago is not what can happen now. So some of it can be advances in technology, but like if you're talking about Johannesburg, where they had the mounds of gold tailings, which some time ago they went, oh, we can process those. So those are disappearing around Joburg, but sometimes you have things that are just too challenging to be anything other than waste. So anyway.
Yeah, I agree. And you kind of hit on one thing too, the ability in an area, you know, like here in the US, I think of like our waste being pretty heavily regulated, especially when you talk about disturbing waste that's already in place. But, you know, that's not the case everywhere. You know, there will be situations where it will be easier
Oh no.
to do an activity somewhere else.
Well, take a look at what's going on in the Fly River, but anyway, that's a whole other situation, right? So
Heather, I have a question. I'm curious about, you know, you hear design for closure, and closures should be, you know, very thought of right up front when you're designing and even before that, a mine. And I'm curious to what extent, kind of using the framework that you've proposed to us, to what extent do you think that could change the initial design? What things might a closure plan reveal about the initial design that may have to be changed?
I think a lot of it, the easiest thing is the post-closure land use, the needs and the wants of the stakeholder can drive, you know, whether you are, I think of next gen, for example. I know I gave that example to show the uranium placement underground in working with over several stakeholder workshops. And even though, you know, uranium tailings have been stored and deposited safely on the surface in the area, it was a precedent. It had been set. The stakeholders themselves were very active and had very, very good reasons why they did not want that, which the closure plan for the post-closure part kind of drove, you know, what type of mining technology we were going to use, so much that it drove us, you know, we were already in an underground mining situation, but it took us to how do we, you know, are we going to temporarily store these waste materials on the surface and then put them back down into the underground workings? Or are we going to now change our operation and put the paste plant directly above what will be a new set of chambers that are independent from the mine itself to get the tailings so that they never really truly leave the plant? They will move from the process facility over to the paste plant, yes, but then they'll move directly down. And a lot of that was influenced by what we had proposed for the closure plan. And there was a lot of concern from the stakeholders there. I think whenever you look at, whenever closure can be part of it, it can be iterative. So the ultimate placement of your waste facilities, for example, where are you going to stockpile your ore? Are you blending? You know, do you need all of those types of stockpiles to? Do you need a waste rock stockpile? Do you need a surface, you know, disturbed TSF? Like the integration of all of those facilities where they're locating changes frequently, even due to the change of, say, the pit or the underground mine, and all going back to the economics. You know, the more material that's generated, the more we'll have to handle. So those facilities become very iterative in themselves in how you even lay them out. And then when you add the closure component of how we're routing water, that comes back all the way to the front then. And the discussions had, you know, over all of these three competing, you know, we've got the actual mining operation, and we've got the material movement part, and then we've got the closure of all of these. So it becomes very integrated.
Thanks.
Any other questions? I feel like I could talk about closure, for the next 30 years.
I guess if we don't have any questions from the audience, I just wanted to say thank you all for attending, and thank you, Heather, for the nice presentation. And I guess we have one comment here. Okay, it's from Dr. Anderson, said very good. Thank you. Okay, and that's all. Thank you very much, everyone.
Cool.
Have a good evening. Stay warm and keep safe.
Thanks, Heather.
Thanks, everyone.
Thanks, Heather. Bye.
Bye.